Hello, everyone. Welcome back to this online class. My name is Francis Okech, and my YouTube channel is Professor Francis Okech. Today, we are going to look at Calculus 1, and our main topic is on applications of differentiation in related rates problems. So we need to understand what we mean by related rates, and then we look at some problems in related rates. So let's take note that I'm going to write. I want us to take note, NB, that if x is a function of t, then dx dt is what we are calling the rate of change of the variable x. This is rate of change of x. X here is a variable. So when you talk of related rates simply means that you have more than one variables and their rates of change are related by an equation. So you can also write this. We can write when two or more variables, when two or more variables, all functions of t, all functions of time t are related by an equation, are related by an equation, comma, the relation between their rates, the relation between their rates, the relation between their rates of change, the rates of change may be obtained by differentiating, may be obtained by differentiating the equation with respect to t. It is implicitly with respect to t. WRT means with respect to. So for example, let me give you a simple example, e.g., if you know that volume is, let's say it is 1 or simply 4/3 by r cubed. Let's say v is equals to 4/3 by r cubed, where 4/3 is a constant, pi is also a constant. If I want to differentiate this with respect to t on both sides, we will have dv dt is equals to 4/3 pi, even pi is a constant, 4/3 pi times derivative of r cubed, which is 3r squared times dr dt. V and R are variables, 4/3 pi, that is a constant. And so when you simplify, you can see 3 will cancel, so that this is the same as 4 pi r squared dr dt. So these are related rates problem. This is a problem connecting the rate of change of volume and the rate of change of radius. So that if we knew that how the volume is changing with respect to time, then it is easy to know how the radius is changing with respect to time. So that let's say given, if you are given, if we are given dv dt, you know that, and also the value of r, comma, then we can find dr dt by the formula, so we make dr dt the subject. This is what we are going to do. Let me take this up. So that if you make it the subject, you're going to get dr dt is equals to 1 over 4 pi r squared times dv dt. So this is an example of a related rates problem. We are using the concept of differentiation to be able to find the rate of change of some variable with respect to time. Now, when you have problems involving related rates, how are you supposed to tackle such kind of problems? So we can write this. We can write to solve related rates, to solve related rates problems, comma, do the following. The first thing you need to do, number one, is to assign symbols. Assign symbols to all quantities given and their respective rates of change. To all quantities given and their respective rates, of change. You can use a sketch where necessary. Use a sketch where necessary. That's the first thing you need to do. Next, the next step is Roman 2. You need to write an equation. Write an equation relating all the variables whose rates of change are given. The rates of change are given or are to be determined. Or are to be determined. The third step is to apply chain rule of differentiation. Apply chain rule Apply chain rule to differentiate implicitly. Differentiate implicitly both sides of the equation with respect to time t. With respect to time t. And then the last thing that you need to do is to substitute into the resulting equation, substitute into the resulting equation, all the known variables, all the known variables and their rates of change. Rates of change, and then solve for the required rate of change. And then solve for the required rate of change. So I'm going to give you an example, but what you need to take note of is when you are faced with a related rates problem, then just need to follow these 4 steps. Those 4 steps will guide you into finding a solution for any given related rates problem. Having explained those steps, let's look at an example of a related rates problem. So you'll write here example number 1. We are told that sand is being emptied. Sand is being emptied from a hopper at a rate of 10 cubic feet per second. At a rate of 10 cubic feet per second. Full stop. The sand forms a conical pile. The sand forms a conical pile whose height is always twice its radius. Whose height is always twice its radius. Full stop. At what rate is the radius? At what rate is the radius of the pile increasing? When its height is 5 feet. That's a question mark. So let's see how to tackle this problem in example 1. We are going to follow the 4 steps to be able to solve this related rates problem. So look at this, a case where we are emptying sand from a hopper. You see, as you continue emptying the sand, it is going to form something like a cone. It's a pile, which is a conical in shape. This cone increases in the radius of the base and also the height as you continue emptying the sand. So we are going to come up with a sketch. You can write here solution. So we need to sketch that cone which we are talking about, and then we'll assign some symbols to represent. One will be radius of the base, another symbol will be that of the height, and another one will be the volume of that cone. So we write here solution. We start by sketching the cone, the conical pile. Something like this. This pile has a radius r. Let the radius be r at any time t, and let the height be h. So we are saying r is radius at time t. H here is the height at time t, and v to be the volume at time t. So look at the information. Sand is being emptied from my hopper at a rate of 10 cubic feet per second. When we are emptying sand from the hopper, it means our conical pile will increase in volume. And something I need to tell you, that when it comes to related rest problem, every time something is increasing, we give it a sign of positive to mean an increase. If a quantity is decreasing, then you're going to denote the sign there by negative. So those ones are very important. Negative here will mean a decrease. So when you look at this information, now we are given that the volume is decreasing. So that is dV dt. It's increasing, I mean, a correction. So because of the increase, we will write positive. It is increasing at the rate of 10 cubic feet per second. We are also told that the height is always twice the radius. We are also told that height is always twice the radius. And what are we asked to find? So we are told to find at what rate is the radius of the pile increasing. Find the rate at which the radius is increasing. That's what we need to find. When height is equals to 5 feet. 5 feet. So I have summarized that information up here. Now, let's see. We are talking of dV dt, which we know, and we need to find dr dt. That means I need to know a relation, an equation relating V and R. And so the question is, how do you find the volume of the cone? The formula for the volume of the cone is that V is equals to 1 over 3 pi R squared H. That is how to find volume of a cone. But because I need a relation, it's a relation between V, R, and H. But look at what I'm given. I'm given dV dt and we are given h in terms of r. So you can use this equation to get rid of one of the variables. Because in this equation, we have three variables. It is easier to reduce the number of variables so that you make your work easy. So I want to get rid of h because we are told h is equals to 2 times radius. So we are going to substitute. Where there is h, we are going to substitute to r. So therefore, what is the volume now? Volume will now be equal to 1 over 3 pi r squared times h, which is 2r. And so when you simplify, you're going to get 2 over 3 pi r cubed. So this is now a relation between volume and the radius r. Let me write this in a better way. So this you could write as, instead of saying equal to, I can just say implies that volume is equals to 2 over 3 pi r cubed. That is the equation that I was talking of, that you need an equation relating the variables that the problem involved. So that's the equation, and that is step 1. Remember, we are saying assign symbols to all quantities given and their respective rates of change, and use a sketch where necessary. Then step 2, we were to write an equation relating all the variables whose rates of change are given or are to be determined. So we have found this is up step 2. The equation I'm talking about is step 2. Of course, step 1 is assigning these symbols and sketching. This is the first step. We go to step 3, where we need to apply chain rule of differentiation to get the rates of change of each of those variables in the equation. So we are going to differentiate this equation. V is equals to 2 over 3 pi r cubed. Remember, V depends on time t, and r also depends on time t. So how do we differentiate? So from this equation, it means that derivative of V with respect to t is equals to 2 over 3 pi, there's a constant, differentiate r cubed, that is 3r squared, then times dr dt. Chain rule, remember, for implicit differentiation, this 3 will cancel, and so this is the same as 2 pi r squared times dr dt. So what do I know? I know dv dt, that is known. I can also get r squared because I know h. So using the value of h, which is 5, it is possible to find r. So we are asked to find dr dt. So we are making that the subject. So hence, what we are asked to find, which is dr dt, is the same as 1 over 2 pi r squared times dv dt. That's how we are going to find our dr dt. Now, you need now to ask yourself that when h is equals to 5 feet, comma, r will be equal to h over 2. Look at the relation that h is equals to r. So r is h over 2, which will mean that this is 5 over 2 feet. Also, we are given that dv dt is positive 10. So when I substitute these values into this equation, I'm going to get 1 over 2 pi, r is 5 over 2, and that's supposed to be squared, then times positive 10, which was dv dt. So when you work out This will be the same as, I can see it is 1 over 2 pi times 25 over 4 times 10, which is the same as 40 over 50 pi. And when you simplify, you get 4 over 5 pi. And because that is radius is measured in feet, so the unit here is feet per second. So, and the result is positive. The positive there means the radius is also increasing. So we can now conclude and say here that, therefore, radius, let me write that in a better way. So therefore, the radius is increasing at a rate of 4 over 5 pi feet per second. Remember, increasing because the sign there is positive. Our value is positive. That's why it is increasing. So you see how this question is very simple. Let me give you another one that is also very, very easy. Example number 2. So I'm going to write it. We write here example 2. So in this example, this is the question. Just a minute, I'm going to write. So the question is this one. We are told that gas is escaping. Gas is escaping from a spherical balloon balloon. Balloon is double L, double O, at the rate of 900. At the rate of 900 centimeters cubed per second. You are asked that how fast is the surface area shrinking when the radius is 360 centimeters. These are question marks. So let's follow the 4 steps. The solution, now you see here, we are talking of a spherical balloon. Is a sphere, and this sphere is losing gas as time goes by. So we are going to sketch the sphere. A sphere, something like a globe, like this one. So that's our sphere. Remember, a sphere has radius. So that is the radius. Another radius is this other side. Radius, and this is the center of the sphere. We can call it O. So what do we know about the sphere? We know because you see it is a balloon and the gas is escaping. So we expect the volume to be decreasing at any time t. So first of all, we need to assign some signs, symbols, I mean. We assign symbols to all the quantities given. So the first symbol is R to mean the radius at time t. You see when the radius is decreasing. So also this V to mean volume at time t, S to mean surface area at time t. So now what are we given? We are told gas is escaping from a spherical balloon at the rate of 900 centimeters cubed per second. That the rate at which the volume is changing, dV dt, is equals to, it is negative 900 centimeters cubed per second. How fast is the surface area shrinking? So we are asked to find ds dt, the rate at which the surface area is shrinking. Find that one. I don't know the values. I'll just put a question mark when the radius r is equals to 360 centimeters. So what do? We need an equation relating V, R, and S, or simply V and S. For us to get the relation between V and S, first of all, we need to know how to find the volume of a sphere and how to find the surface area of a sphere. So we start with volume. We know that volume of a sphere is given by 4 over 3 pi r cubed. That is the formula for finding the volume of a sphere. 4 over 3 pi r cubed. What about the surface area? Surface area of a sphere is given by 4 pi r squared. Those formulas, you must know them. So here now we have two equations. The third step, let us differentiate each of these equations implicitly with respect to time. I'm going to differentiate this. Let me bracket it. We will also differentiate the equation for S and R. Let's start by differentiating the first equation. You write here dV dt is equals to 4 over 3 pi times 3r squared dr dt, which if you simplify, this and this will cancel. If you simplify, you're going to get this is equals to 4 pi r squared times dr dt. And so therefore, you can make dr dt the subject. You can say therefore dr dt from this equation is 1 over 4 pi r squared, then times dv dt. That's what we have. Let's do the same to the other equation. If I differentiate s, we get ds dt is equals to 4 pi times 2r times dr dt. If you simplify, you're going to get 8 pi r times dr dt. Again, from here, you can just say, therefore, from this one, dr dt is the same as 1 over 8 pi r times ds dt. So look at those two equations. Let me tick them. Look at this equation and this one. We can now equate them because on the left-hand side, we have dr dt. So equate those two equations. So you can say, hence, 1 over 4 pi r squared dv dt is equals to 1 over 8 pi r times ds dt. And from here now you can make ds dt the subject. So this implies that ds dt is equals to, I'm multiplying by 8 pi r. 8 pi r over 4 pi r squared dv dt, which means if I simplify this further, I'm going to get ds dt is equals to, of course, in the numerator we'll have 2, the denominator will have r, then times dv dt. That is the relation between s and v. So, and you see the task is to find ds dt. That's why we are eliminating dr dt, because we don't need to find dr dt. We are interested in ds dt given dv dt and r. So now when you substitute what you are given, so we now substitute the value of r. We are told r is 360 and dv dt was negative 900. So upon substitution, so you can write substitute r and dv dt to get, so what are we going to get? We are going to get ds dt is equals to 2 over 360 times negative 900. You can simplify this. 2 over 360 times negative 900, that should give you negative 5. This is the rate of change of surface area, so this is centimeter square per second. That means the surface area is decreasing at the rate of 5 centimeters square per second. So we can now conclude here and say here that therefore the surface area is decreasing, this is the spelling, decreasing at the rate of 5 centimeters square per second. So that's what we have as our answer in problem number 2. Let me give you another problem. Example number 3. So as you can see, these related rest problems are very, very simple. As long as you know the formulas that are needed and you're able to link those variables to form an equation. So let's look at example number 3. So in example number 3, we are told that we have two cars, A and B, and the first car A is traveling due west at 50 kilometers per hour, and the other car B is traveling due north at 60 kilometers per hour. Both cars are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 kilometer and car B is 0.4 kilometer from the intersection? That should be a question mark. So we'll have a question mark here. So let's see how to go about this problem. We need to sketch how these cars are moving. One is moving towards the west and one is moving towards the north. That is from the south towards the north. One is moving from the east towards the west. So this is how the intersection looks like. The one that is moving towards the west is in this direction. In this direction. The one that is moving towards the north is moving in this direction. So this is the intersection of the two roads. Let me call it point C. Let this point be A, and let this point be B. So I can join A to B. And you see this thing here, let me use another color. This is a right angle triangle. So this is car A moving towards the intersection, and the other one is car B moving towards the intersection. Now, I don't know the speed at any time t. So we are going to say let the speed here, or the distance, be x kilometer. That is from where A is to the intersection, and that of B to be y kilometer. X kilometer, here it is y kilometer. So let me rub that and write kilometer. Minute. So this one is y kilometers. Y kilometer. So what are we saying? That let x be the distance of car A and y be the distance of car B from the intersection. The intersection is at point C, and that is at any time t. So let me explain here that x is distance from A to C at time t. What we are calling y is the distance from B to C at time t. You see, x and y depend on time t, because as the two cars are moving, the distance keep on reducing or shrinking. So what about the distance between B and A? So let Z be the distance from A to B at any time t. So this one here is Z. Now look at that triangle. It is possible to find an equation relating x, y, and z. But before we look at the equation, what are we given? We are told that, you know, when you talk of speed, is distance over time. The rate of change of distance, that is what we are calling the speed. So in the question, we are told that car A is traveling due west at 50 kilometers per hour. And car B is traveling due north at 60 kilometers per hour. So that simply means that dx dt, which is the speed, you see it is negative because x is decreasing. So negative 50 kilometer per hour. We also told that dy dt, because again y is decreasing as the other car is moving. Again, what we know is that dy dt is negative 60 kilometer per hour. So we are required to find, because we are told at what rate are the cars approaching each other when A is 0.3 kilometer and B is 0.4 kilometer from the intersection. So we need to know dz dt. We don't know this. That's what we need to find. 2 question marks. When x, the distance from A to C, when x is 0.3 kilometer, that should be 0.3. Let me write that in a proper way. 0.3 kilometer, and y is equals to 0.4 kilometer. So that is step one. Step two, let's come up with an equation relating x, y, and z, of course, at any time t. If you look at our triangle, we can deduce from the Pythagoras theorem that z squared is equals to x squared plus y squared. That is from Pythagoras theorem. Now, that is the equation relating those two. Step three, now we need to differentiate this equation. Let me bracket it. This is the equation that we need to differentiate. So I can change, I can select another color. Let me pick black. So what about the derivative of this equation with respect to time t on both sides? So you can write here that on the left-hand side, it will give us 2z times dz dt. On the right-hand side, we are going to get 2x times dx dt plus 2y times dy dt. And you see 2 is common, so that will cancel out. You can make dz dt the subject. Make dz dt the subject, so you can say or dz dt is equals to, let me pick another color, So I can pick red. So we say or dz dt is equals to, we are dividing by 2z, so that is x over z times dx dt plus y over z times dy dt. So when you look at that equation, we know dx dt, we know dy dt, we know x and y, but do we know z? No. We need to find z. Because we don't know z, let's see, how do we find z when x is 0.3 and y is 0.4? So I'm going to write this, that you can say but when x is 0.3, comma, y is 0.4, 0.4, we have, what is z? Let's calculate z. Z is equals to, of course, z squared is x squared plus y squared, so that will give us the square root, because I need to find z. Square root of 0.3 squared plus 0.4 squared. So this will give you 0.5. When you press that in the calculator, you get 0.5. Now that we know everything, let us substitute the values of x, y, z, dx, dt, and also dy, dt. So you can now say therefore, dz dt is the same as x, which is 0.3, over z, which is 0.5. Dx dt was negative 50, plus, now we know y to be 0.4, z is 0.5, dy dt is negative 60. So we need to press this in our calculator. When you work it out, you need to get dz dt is equals to negative 78. So the result is negative 78. The negative there means a decrease. So this negative 78 kilometer per hour. So that is the rate at which the two cars are approaching each other when A is 0.3 kilometer and B is 0.4 kilometer from the intersection. Then there is a decrease because they're approaching each other. So they are trying to minimize the distance between them or to reduce that distance between them. So that is all about question number 3. Lastly, let me give you another one. We can write example 4. Example number 4. I want to exhaust all the problems involved in related rates. So the last example is example number 4. So in example number 4, we are told that water is running out of a conical funnel at the rate of 5 centimeters cubed per second. If the radius of the base of the funnel is 10 centimeters and the altitude is 20 centimeters, find the rate at which the water level is dropping when it is 5 centimeters from the top. So as usual, we are going to sketch this kind of a funnel. You see now, this is now a funnel where the base area is now at the top because it is like a cone that is tilted upside down. So the base is now at the top. So we draw the base at the top. Then the vertex of the cone at the bottom. So that is a funnel of that shape. Now, at any time t, the radius of the base is r, and the height is h. That is at any time t. But you see, this is a cone, a funnel where the radius is 10 and the height is 20. So initially, let me just change this. Instead of h, I'm going to write 20. Let me use another color. This is 20 initially, and the radius initially is, instead of r, we can use 10. Initially, the radius is 10. So this is a circle. Then here we have 10. Even this one, I can write it here. The height initially is 20. Now, as the water is moving, you see it will reach a point where the funnel will not have any amount of water because the water is running out of a conical funnel. And so at that rate, the volume at which the water is decreasing is 5 centimeters cube per second. So at any time t, let the radius be r and let the height be h. This is h, height, and this is radius r. That is radius r. So r here is radius of the water surface at time t. So r is the radius of the water surface at time t. What about h is the height of the water surface at time t. Of course, the height from the surface of the water to the vertex, the sharp point. That's what we're calling h. Let V be the volume. Volume of water in the cone at time t. And that is at time t. So now we know those symbols. What are we given? You need to take note of what you have been given. We are given that the rate at which the volume is changing with respect to time is 5 centimeters cube per second. You see the volume is decreasing, so that's negative. It's a negative 5 centimeters cubed per second because the volume is decreasing. Per second. We also told that radius initially is 10 and the initial height of that cone, or simply the water surface, is 20 initially. That is simply the radius when the time is 0 and the height when the time is 0. So what are we required to find? The task is to find the rate at which the height is decreasing. So that is dh dt. We don't know this, so I'll just have some question marks. We want to find dh dt when the height is equals to 5 centimeters from the top. From the top. That's what we are told. Now look at these values of r and h. That will help you get the relation between r and h. When r is 10, h is equals to 20. So from here, it is clear that h, when I divide by r, is 20 over 10, which is the same as 2. Or h is equals to twice times the radius. H is twice radius. That's very important. Now, what is the formula for finding the volume of a cone? Volume of a cone is the same as 1/3 pi r squared h. Because I need a relation between volume and height, so I'll get rid of the radius. You see, from this formula, it means radius is equals to height over 2. So I'm going to substitute it here into our expression for volume. So that is 1/3 pi, then the radius squared. So that is h over 2 squared times another h. But 1/3 pi r squared h. So we are replacing r. So what are we going to get if we simplify? We are going to get 1/3. If I expand this one, that's pi h squared over 4 times another h, which is equals to, that is now pi over 12, or simply 1/12. That's 1/12 pi h cubed. So that is the volume as a function of h only. Volume as a function of h only. Pi over 12 h cubed. So I can just write it here as a summary. You say, therefore, volume can now be written as pi, that this should be pi over 12 h cubed. So now let's differentiate this equation with respect to time on both sides. Let me bracket it. Now I want to know the derivative of this equation with respect to time. So we are saying dv dt is equals to, remember, pi over 12 is a constant. That's pi over 12 times derivative of h cubed, which is 3h squared times dh dt. So that's when you differentiate. And you see, you can simplify. When you simplify, you're going to get pi over 4 h squared dh dt. Now, make dh dt the subject. When you make dh dt the subject, let me write hence. So we are going to make dh dt the subject. That means I divide by pi over 4 times h squared. So hence, we can now write that dh dt is equals to, when you cross multiply, that will be 4 over pi h squared times dv dt. Now, h is measured from the water surface to the vertex of the cone. But look at what we are given. We are told to find dh dt when h is 5 centimeters from the top. So then, what is the distance from the water surface to the vertex if it is 5 centimeters from the top to the water surface? So therefore, we are saying that we need to find h, dh dt, I mean, when now h is equals to, the trick here, don't put h is equals to 5, but it should be 20 minus 5, because we are given the distance from the top, but h is the distance from the vertex of the cone. So in this case, h must be 15 centimeters. H is 15 centimeters now from the bottom, from the vertex. So you put h is 15. We also told dv dt to be -5. So when we make the substitution, we are going to get this. Remember, the negative is very important where we have dv dt, because the negative there denotes a decrease. So we'll have dh dt to be 4 over pi times h squared, that is 15, and you square it, then times dv dt, which is -5. You can press this in your calculator. Leave your answer in terms of pi. So that means in the numerator, because I'll be having -20 over 15 squared is the same as, let me write here, -20. 15 squared is the same as 225 pi, of which if I divide by 5, both numerator and denominator, I'll get -4 over 45 pi. And this is dh dt. H is measured in centimeter, so this is centimeter per second. The negative means that even the height is decreasing. So then, to conclude on this one, you can now say that the water level is dropping at the rate of 4 over 45 pi centimeters per second when it is 5 centimeters from the top. So those 4 problems, example 1 all the way up to example 4, are problems you can encounter when you deal with related rates problems. Thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, to share, and also to like this video. When we meet next time, we look at other applications of differentiation in real life situation. So let's meet next time. Bye-bye.